Hello teacher, my name is Steve and I'm from Group Friday. My members are Miss Phương and Mr. Sang. So our group's seminar is about global and local kernels for recommender systems. So our presentation will include 5 sections. The first 2 sections presented by me are introduction, autoencoders meet collaborative filtering. This one is abbreviated by auto-rate, and the next one presented by Ms. Phương, and the last 2 sections presented by Mr. Sang. So now for the first one, introduction. So I would like to talk about the objective of our group seminar. We want to research the model I-auto-rate. This one stands for item autoencoders meet collaborative filtering, and this model is presented in the recent paper GlocalK, Global and Local Kernels for Recommender Systems. So, as you might know, we can use neural networks to collaborative filtering, and some traditional neural networks they use autoencoder models to generalize sparsely observed matrix entries. This one to a low-dimensional feature space like this. How about our model I-auto-rate? So this model also uses autoencoder, but with the purpose of taking high-dimensional matrix entries, projecting them into a low-dimensional latent hidden space, and then reconstruct the entries in the output space to predict missing rating. And this model focuses on the extraction performance by using 2 types of kernels, local kernel and global kernel. So the picture below over here illustrates for our model I-auto-rate. This model uses autoencoder twice, the first one over here and the second one over here, and local kernel and glocal over here. So now we will go into details of this model. So when we learn about collaborative filtering, we also learn some denotation for this algorithm. We use M to indicate the number of users. We use N to indicate the number of items. And then we build a utility matrix R with the shape N times N. So the user U belongs to the set of users from user 1 to user N, and each user can be represented by the vector R. So RU will include the elements representing for the rating. So the rating for the N items. So for example, RU1 over here means the rating of user U for item 1. In the similar way, we can build each vector for each item. So for the item I, we can build a vector Ri for it. So the R1I over here means the rating from user 1 for item I. Okay, and so before we jump into the I-auto-rate, we will review a little bit about the model autoencoder. So remember, we built the I-auto-rate using autoencoder. So it's necessary it's necessary for us to review the model autoencoder. So the objective function of the autoencoder is this. So we try to minimize the distance, the difference between the input R and the predicted H over here. So the formula for the reconstruction H is the activation function f of the weight times another activation function t, and then plus bias b. So on the right hand side is the image illustrating for these two formulas. So at the beginning we have the input R, because we have m users, so this factor include m elements, and we use m naught in the input layer to represent this m ratings. Okay, so the shaded circle means we already have the value, but the unshaded circle means we haven't had the rating. And then we have the first bias over here, the weight V times the input R, and then plus the first bias, we get the result before the hidden layer. And then this result under the first activation function T, we get T of VR plus the first bias. And then this result times by the weight W, and then plus the second bias, we get another result. And this result under the second activation function will give us the predicted rating. So you see over here. So, and one more question we can raise over here is that what is the total number of parameters of the autoencoder model? So we denote all of the parameters by the theta, and the theta will be updated by backpropagation. We use backpropagation to calculate the gradient, and then we use the gradient to update the parameters theta. So get back to our question. The total number of parameters in this model. So we see at the beginning we have m nodes, so that's why we need m weights V, and then because we have k nodes of hidden layer, so that's why the total number of parameters between the input layer and the hidden layer is m times k. And between the hidden layer and the output layer, we also have m times k parameters. So in total, we have 2 mk parameters. And then because each hidden layer and output layer has their corresponding bias, so that's why the total number parameter of this model is 2 mk plus m plus k. So now we move on to the GlocalK model. So the GlocalK model will modify the objective function of the autoencoder. So we just consider the contribution of observed rating. So that's why we use this norm to calculate the distance between the input and the predicted rating H. And in order to avoid the overfitting situation, we add the regularization with the learning rate being lambda. And because we have two types of weight, W and V, so we add them over here. And the total number of parameters of this model is also 2mk plus m plus k. Yeah. Okay. And now for a particular parameter theta over here, the predicted rating for user U for item I is this. So after we know the autoencoder, we know I autorate, we will go into detail of two kernels, their advantage in the I autorate in the next part.
Move to the section 3, the global and local kernels for recommender system. The purpose is to improve the feature extraction performance for high-dimensional user item rating matrix into a low-dimensional latent feature space. We apply two types of kernel that have strong ability in feature abstraction. The first kernel, known as local kernels, it gives optimal separating surface to perform the data transformation from high-dimensional space, and it's widely used with the support vector machines. And the second kernel, known as global kernel, from convolutional neural networks architectures. This is the global local kernel-based matrix completion framework, or GlocalK, and the first part here is the pre-training the autoencoder using a global kernelized weight matrix. And the second part and the third part here is the fine-tuning with the global kernel-based rating matrix. I will go deep dive into the first part with the pre-training the autoencoder using a local kernelized weight matrix. This part is to make dense connections denser and sparse connections sparser using a finite support kernels. The input is the vector Ri and the output is the reconstructed vector Ri dash to predict the missing ratings with the following formulas. While the WE and WD are the weight matrix, B and B dash are the bias vector, FG are non-linear activation functions. We apply the local kernel-based weight matrix here to using encoder and decoder here. To explain it more detail, the autoencoder deploys an auto-associative neural network with a single edge dimensional hidden layer, and to emphasize the dense and sparse connection, we reparameterize weight matrix in the autoencoder with a radio basic functions kernel. The local kernelized weight matrix, the radio basic function kernel can be defined as the following functions, and this kernel function computes the similarity between the two sets of vector U and V. As the output, each element maps to 1 for identical vector and approach 0 for very distant vector between U and V. And this is the formula of the local kernelized weight matrix. And the distance between vector of U and V determines the connection of neurons in neural networks and the degrees of the vector as changed in each step of training. As the result, applying the kernel trick to weight matrix to regularize weight matrix and learn generalizable representations. As the following step is the fine-tuning with the global kernel. With the output of the pre-training model is the vector R in the previous step. We pass to the pooling with item-based average pooling using the formula to interpret as item-based summarizations. and this number six formula. This kernel are accurate by using an inner product as rating dependent mechanism. So and the matrix R is the global kernel based rating matrix, denotes a convolution operation, and with this we use as the input for the fine tuning auto, and we using the autoencoder fine tuning in this matrix, and the final predicting rating for matrix completion in recommender system.
Now we come to the implementation part of the seminar. We did the experiment with two completion dataset of movie length. The first one is the movie length 100K, and we did not add ML 100K, and the other is movie length 1 million, did not add ML 1 million. For reading the dataset for the ML 100K, it includes 100,000 rating of 1,682 movie made by 945 users. The dataset in the ML100K, there are several files for training and testing, and the file with extension .base is used for training and .test is used for testing. And we use two typical files, that is UA.base and UA.test for training and for testing. And for the ML 1 million, it's a little bit different. It includes 1 million rating up 3,706 movies made by more than 6,000 users. And in the movie 1 million, it keeps the rating matrix in a single file, so that we have to rate and split the file into two subsets with the ratio 90 and 10 for training and for testing. And for the environmental setup, we choose Google Colab as an environment for training the model. User can easily create a Python notebook, which is quite similar to the Jupyter notebook in just a few clicks. Colab also provides for every user a free GPU, which can help users accelerate their training process. And Colab also provides with many different libraries like TensorFlow, PyTorch, Keras, or OpenCV. And you do not need any external configuration when using the library. You just import and coding on it. It's quite easy for sharing and modifying. Now come to the hyperparameter setup. Before the training process, we have defined some hyperparameter. First, we define a 500-dimensional hidden layer for the autoencoder, 5-dimensional vector u and v for the radial basic function kernel. For the fine-tuning process, only a single convolution layer with a global convolution kernel upside 3 by 3 has been applied, and the LBFGSB optimizer have been used to modify the regularized square error, where L2 is applied with different penalty parameter. And here is the code implementation. First, we have defined a RBF kernel function which compute the similarity between two sets of vector u and vector v. And in the kernel layer, u and v are two randomized vectors, so that we can calculate W hat from u and v, and the new WEFF is calculated from W hat, and W is the original weight matrix. After that, we will do a matrix multiplication between the original rating matrix with the WEFF, and then we plus with the bias vector. After that, we will pass them through an activation function so that we will have a reconstruct matrix for the retraining step. And for the fine tuning, after we have a reconstructed matrix from the retraining, we can apply item-based average pooling to summarize each item information in the rating matrix, and then we define several randomized kernels, and these kernels are aggregated by using an inner product with the average pooling matrix we already get before. After that, we will combine them together so that we can get a global kernel. This global kernel will be applied a convolution operation to the user item rating matrix for the global kernel-based feature instruction later. And the next part of the seminar is the evaluation. First, we want to analyze the effect of the retraining. We try to explore the optimum number of epochs for retraining on ML100K and ML1 million, and we running them with 60 epochs total. And we can see that they share the same bowl-shaped curve during the running process. First, the root mean square error is decreased when the epoch starting from 0. However, when it reaches the optimal point, it tends to increase in both datasets so that we can give a summary. Having more item number with lower density may lead to less retraining for optimal performance. And next is some measurement for the ML100K and ML1 million, the training process. First, for the ML100K, it running in total 90 box. For the retraining, the average time is 4.2 seconds, and the test root mean square error is 0.93, and for the fine tuning, the average time is 8.7 seconds, and the test root mean square error is 0.91. So that in the ML100K, the best record of root mean square error we receive is 0.91. For the ML1 million, the retraining process running in nearly 72 seconds, and for the fine tuning it running in nearly 48 seconds. The test root mean square error for the retraining is 0.82, and test root mean square error for the fine tuning is also 0.82, so that the best record of root mean square error in the ML1 million is 0.82. Based on the information, we can give you some summarize. Firstly, the training process time it tends to scale with the size of the dataset. The more data, the slower the process. And during the pre-training and the fine-tuning, it has some improvement of the root mean square error because the root mean square error has been decreased. And with the more data, we can see that the root mean square error tend to decrease. It means the performance of the algorithm become better. And finally, it comes to the end of the presentation. Thank you for your listening.